Hey everybody, let's look at this one right here, which is meant to teach us something called the continuity equation. And so what they tell us here is that we've got this piece of water, if you want to call it that, moving through this pipe right here, and that we've got another piece of water moving through this constricted section of the pipe. They say the area of this pipe, the cross-sectional area, is A1, and the cross-sectional area of this constricted part of the pipe is A2. This little piece of water has got a length of L1, and this piece of water has the same volume as that piece of water. And in order for that to happen, it needs a length of L2 there. And so they ask us to say, how do A1, A2, L1, and L2 relate? So more explicitly what they're saying is that the volume of section 1 has got to equal the volume of section 2. And these are capital V's for volume, not lowercase v's for velocity. So if they each have equal volumes, which they say they do, then we just need to think about how we find the volume of a cylinder. And we take the area of the base times its height. So this volume is A1 times L1, and that has got to be equal to A2 times L2. Now, they say if the water that passes this point in a given section time t is the same as the volume of water that passes by this section of the pipe in time t, then rewrite this in terms of keeping it in mind as a rate. So in other words, the volume per time in section 1 has got to equal the volume per time in section 2 there. If not, we would be gaining mass or losing mass in one section of the pipe, and this pipe is uniformly filled with an incompressible fluid. We already made these substitutions for volume here, so we can say area 1 times length 1 over the time has got to equal area 2 times length 2 over the time. So all we're doing is making this a rate here. Next up, they say, and I'm going to put this here for a second before I bring the other one back. It says rewrite those expressions taking into account that the speed of the flowing water is velocity is equal to L over T. So a length over a time is a velocity. Well, look, here we have a length and a time, and here we have a length and a time. And so why don't we rename these guys right here? So length 1 over time, let's call that velocity 1. And so when we go to rewrite this, we will get area 1 times velocity 1, that's a small v for velocity, has got to equal area 2 times velocity 2. This equation right here is known as the continuity equation, and is basically saying that there's a constant volume flow rate everywhere in the pipe. All right, now let's do one here. They love involving horizontal projectile problems into these. So it says we've got a rectangular waterway right here, a sluice. It's got a width here of 0.5 meters. It's got a depth right here of 0.12 meters. The water passes over the precipice at 2.7 meters high. So that's the height right here. And it lands, it says 0.68 meters away. So it goes off this 2.7 meter high cliff, and it lands 0.68 meters from the base of the cliff. So how fast is the water going when it goes over, it crests the precipice, so it comes out right here. So what we are going to do, we are going to figure out, this is a horizontal projectile problem. So the velocity in the x direction will equal our displacement in the x direction over the time it takes to fall. Now, we don't know the time it takes to fall. We always use the third kinematic equation to solve for this. That's going to be in the vertical world. So our delta y is equal to our v0y times t plus 1/2 times our y acceleration, which is g, times the time squared. This initial y velocity for a horizontal projectile is 0. So when we rearrange this equation, we get time is equal to the square root of 2 times the height over the acceleration due to gravity. So let's plug in some numbers here. So our time then will equal the square root of 2 times, technically our delta y is a negative, right? Negative 2.7 meters because it goes down, but our acceleration's also a negative, so those will cancel out over negative 10. That will give us a time there of 0.7 0.73 seconds. So last step then we need to do is come all the way back to here and find that our velocity in the x direction is our x displacement, which is 0.68 meters, divided by the time it took to fall, which was 0.73 seconds. And so our x velocity is 0.93 meters per second is the speed that is coming off of that cliff there. Last part here, or last two parts, sorry, they say, what is the volume flow rate of the water in the sluice? Well, remember, volume flow rate, or volume over time, is the same thing as area times velocity. And the area for this sluice is this area like right here. And so that's going to be the width times the depth there. So width times depth times velocity will give us the volume flow rate there. They told us that the width of this was 0.5 meters. They said the depth of it was 0.12 meters, and we just solved for the velocity, which was 0.93 meters per second. So once we multiply all of those together, we should get a volume flow rate. By the way, you could write that as V over T. Sometimes you'll see it written as Q. Sometimes you'll see it written as this weird V like this. But let's just say the volume flow rate here is 0.0558 cubic meters per second here, because a meter, and then the seconds left over. All right, last part here. How long would this take to fill an 8 cubic meter storage tank? Well, if the volume flow rate, or let's call it Q here, then to solve for the time, multiply time up here, divide Q down here, we would take the volume we're trying to fill divided by the volume flow rate. So we're trying to fill 8 cubic meters. We're filling it up at a rate of 0.0558 cubic meters per second. And so when you work that out, you'd get about 143 seconds.